Good evening. My name is Dr. Shakti, and we're going to be starting with revision series on your nerve muscle physiology. So today we'll be focusing on nerve, and then the next class we'll be focusing on some muscles. So we'll just take a look at some questions that have been given. So you can see here, out of these, in relation to the topics we're going to be discussing today, we have generation and propagation of action potential in a neuron, the all or none principle, role of neurotransmitters in nervous system. The remaining questions will be doing it in the next class. So again, I'm gonna divide the topics today for nerves and in the next class, muscles. So I'll be also telling you what are the probable questions that come from these topics. So in nerve, we have to start off with your RMP. So this can come as a short note by itself. Then your action potential. This is another short note, or it can come even as a long question. So in action potential, what do they ask? You have to define what an action potential is. We have to draw, label the various phases, then the mechanism behind each phase. Then we have to talk about the properties. And sometimes there might be a question, what is the difference between action potential versus graded potential? So from this topic, these are the various important questions that keeps repeating all the time. Okay. So we'll start off with your RMP. What is your resting membrane potential? That is the membrane potential. So you have a membrane, and that across the membrane, you have a negativity over here, positively charged ion here. So this will result in a potential difference across the membrane. And this is because of something called Donan effect. Why? Because of the presence of non-diffusible ions. What does it mean? We have large charge particles like protein, which are here on the inside, which cannot come outside. So equilibrium is never attained over there. So instead, what will happen? Your positively charged ions from the outside will come and line up against it like this. And all the negatively charged ions will be here. So if we were to put certain electrodes and measure the potential difference across the membrane, you would get your resting membrane potential. So at rest, the membrane potential which is existing, that is your resting membrane potential. Now, how is resting membrane potential generated so like that? That is because of the presence of your potassium channels. So imagine here, there is a leaky potassium channel. When a leaky potassium channel is there, that will result in potassium efflux. A potassium efflux will make the inside negative. A positively charged ion is going outside, and it will make the inside negative. And that inner negative ion, which is large protein which cannot cross, that will result in the Donan effect now. And hence, there is inequitable distribution ions across the membrane, resulting in a negative resting membrane potential. So RMP is usually negative. It goes to around minus 90 in your skeletal muscles. Neurons also, if you take a look at smaller neurons, it is usually minus 70 millivolt. But larger neurons can have minus 90 millivolt. And then we have smooth muscle. Smooth muscle has undulating, changing RMP, which is in the range of, minus 45 to minus 65 millivolt. And on an average, we say around minus 55 millivolt. So this is the various values of RMP. If a question of RMP is coming, you have to mention about the Donan effect. You have to mention about the inequitable distribution of ions. You have to mention how it is the generation of RMP is done by a leaky potassium channel, which results in the RMP being negative, and give the values of minus 90 millivolt in skeletal muscle, small neurons minus 70, large neurons minus 90, smooth muscles minus 55, but on an average, the range can be minus 45 to minus 65. Apart from that, there is another thing, apart from generation, what is resulting in the maintenance of RMP. So RMP maintenance is because of your sodium, potassium, ATPase. So what does it do? Sodium, potassium, ATPase results in 3 sodium and 2 potassium. So even if some positively charged ion, most likely sodium, is coming inside, that will be taken outside. So this is in effect a 3:2 ratio electrogenic pump. So that is going to result in 1 extra positively charged ion going out, hence maintaining the negativity inside. Okay, so generation of the RMP is by leaky potassium channel. Maintenance of the RMP is by sodium potassium ATPase. If a question of RMP is coming, these are the various points that you have to mention and write the answer. Okay, next is understanding your action potential. So first we have to define action potential. So action potential can be defined as a brief sequence. So it's a brief change, okay, not a permanent one, a brief sequence of changes to the membrane potential. So membrane potential keeps changing during this period. Okay, so there is a whole sequence of changes toward the membrane potential in response to a threshold or above threshold stimulus. If we give a stimulus which is either threshold or above threshold, that will result in a brief sequence of changes in the membrane potential. That is what we call action potential. Now, earlier we were asking, what is the difference between action potential and your graded potential? So graded potentials are different, that it does not have to be a threshold or above threshold stimulus. It can be any stimulus. Okay, so graded potentials, not by your threshold stimulus. It's not reaching the threshold. So the changes in action potential is happening, but it is not because of above thresholds or threshold stimulus, because of which the nature of this is something that dies off eventually. This wave which is propagating, which will not keep going, instead it will die off. The thing is, in action potential, this wave, it starts from one point, it keeps going and going till the end. But a graded potential is often localized and does not propagate much. Okay, so these are brief sequence of changes by below threshold stimulus, which are localized to a confined area and does not propagate. That is a graded potential. Okay, so difference between action potential and graded potential. We defined also what is action potential. Now draw, label a action potential. So if you have to draw and label an action potential, first you have to start off with when you're giving a stimulus. Okay, so at some point you're gonna give a stimulus. After that, there is a small period of latent period. After the latent period, what is going to happen? So say this is at minus 70 millivolt. From minus 70 millivolt, it will go up. And say, for example, it reaches minus 45 millivolt. And at that point, it is going to go up as a spike potential. It'll cross 0, it'll go till plus 30, in around plus 30. At which point, it is now going to come back down. It keeps coming back down. At some point, it will slow down and then it'll go into hyperpolarization. And then it goes and eventually reaches your RMP. So what are the different phases that are here? One, this whole area is depolarization. And over here, we have the repolarization. This is going to be your threshold. Okay. Now, in repolarization, there is this area from here till it reaches its RMP. This is called after depolarization. That is called after depolarization. And the part below that, which goes even more negative compared to your RMP, that is going to be hyperpolarization. From here till here, that is what is called hyperpolarization. So these are the different phases. You can mark the scaling over here and you can label them. Now you have to describe it. Okay, so you draw a label. Now you have to explain the mechanism of each phase. How does it happen? So the first thing, when you give a depolarizing stimulus, we have a latent period. Why does a latent period happen? Because of the latency for activation. So what happens when a stimulus is given? You have to open up a sodium channel or any other non-specific channel. Some time will be taken for opening up of an ion channel. Okay, so for that configuration changes should be required. So in this regard, and after opening up the ion channel, ions has to flow in. Okay, so all of that will result in latency in this scenario. After the latency, what is going to happen? Initially, there will be a part where, because of sodium influx, the potential will go up. It's much slower, as you can see over here. And once it reaches threshold, then at that particular voltage, there are a group of voltage gated sodium channels. Not your regular sodium channel like this, but they are voltage gated, which means it understands that, okay, it has crossed minus 45. Threshold has been crossed. So it will get activated. Now, why it's going as a spike potential and keeping on going is because there is a feedback mechanism. What kind of feedback mechanism? It is an example of a positive feedback mechanism. So what is happening here? One, voltage gated sodium channel activated, which means sodium influx is happening. Sodium influx is happening, move positive. So the membrane potential changes further, making it go more towards the positive side, which means that will again reinforce whatever remaining voltage gated sodium channels are there to keep opening up, which means more sodium influx, which again will keep making this loop go ahead. So this is an example of a positive feedback cycle that you see, resulting in a depolarization. It goes above 0, which is called overshoot. And usually it goes to around plus 30. Now, at this point, what is going to happen? there is going to be activation. The same stimulus that resulted in opening up of your sodium channels, same stimulus after a gap, because it takes longer time for configurational changes in your potassium channels, it will get activated after a gap. Hence, at some point over here, your potassium channels will get opened up. When potassium channels get opened up, potassium is more inside and hence potassium will go outside. Earlier, during depolarization, when a sodium channel was opened up, sodium was more outside, so sodium will come inside. But when a potassium channel is opened up, potassium is more inside the cell. Hence, potassium will go outside. So for depolarization, sodium influx. For repolarization, potassium efflux. Now, this channel which is opened up, this potassium channel which is opened up and resulting in potassium efflux. At some point, the rate of flow is still governed by your fixed law. J is proportional to delta C into area by thickness. So delta C is concentration gradient. So if because of this, potassium kept going outside, eventually it is nearing its equilibrium stage. Okay, so here potassium is much more over here. And this is the amount of potassium here. Now you open up a channel over here. What is going to happen? Potassium will come. Potassium will keep going. Now look at the difference. The gradient has decreased. Now it's reached equilibrium. Okay, say it is this much now. Now one more has come. So what happens is, as more and more of potassium goes to the other side, this gradient declines. As the gradient declines, the rate of flow declines. That is why, especially at some point, you see that it becomes lower. That phase where the rate of flux is reducing during repolarization, that is called after depolarization. And then after that, what happens? This potassium channel which opened up, it reached its equilibrium potential. And it has reached over here at your RMP. Now, instead of stopping, it is keeping on going. Just think of inertia. The thing is, this once it starts to realize, okay, we have reached our equilibrium potential, it's time to stop this. By the time the configurational changes stop all the potassium channels, it would have allowed more potassium to go outside, resulting in it being extra negative. And hence, it reaches here. And then, by your normal mechanisms of generation and maintenance of RMP, your RMP comes back. So these are the various phases: latent period, the depolarization, overshoot, repolarization after depolarization, hyperpolarization, and return back to the resting membrane potential. These are things that you have to talk about when explaining mechanism of each phase. So for example, this is 1 mark. Draw and label can be 2 mark. Mechanism of each phase can be asked as a 3 mark. Okay, that is already 5 mark question. On top of that, if they want to put this as an essay, RMP, 2 marks. That is 7 marks. Remaining 3 marks you put for properties. This is now a 10 mark question. Or separately, each of them can be asked as a short note by itself. Sometimes draw and label and mechanism of each phase. This can be asked as a 5 mark question. In which case you have to know this will give you 2 marks, this will give you 3 marks. So accordingly, learn to write based on how much marks the questions are asked for. Okay, so these are the most important 2 questions that will be asked from your now finally, we have to talk about the properties. So when we talk about the properties, what are the properties we have to talk about? Properties, you can talk about excitability. Then you can talk about all or none law. Then you can talk about conductivity. Then you can talk about refractory period. You can talk about accommodation. You can talk about the fact that it is infatigable. Then you can talk about property of mixedness and even width of denervation, hypersensitivity. These are the properties you have to talk about. If you can't remember much, excitability, all and low conductivity, refractory period, accommodation. At least this much I want you to remember. Okay. Separately, sometimes property of mixed nerve can be asked as a question. So these are the ones, at least I want you to remember for the exam. So under excitability, what is excitability? The ability of a tissue to respond to an external stimulus. So when you stimulate an object, the ability of that object to respond to a excitable stimulus, that is excitable. Okay, so this is where we have to talk about your strength, duration curve. If we talk about your strength, duration curve, the strength of the stimulus and the duration, how long you're going to give it. So usually this curve is going to be like this. Beyond this point, so there'll be a minimum strength that you have to give, regardless of how much duration you give. Even for infinite duration, you give, there should be a minimum strength of stimulus that needs to be given. Okay. Then this strength that you have, double the strength of that and the duration that you have to give it for. That is an important terminology. That is called chronaxy. So chronaxy is a unit of excitability. Now, using chronaxy, you can measure different objects, look at their chronaxy levels and say, okay, this tissue is more excitable compared to this one. And for the same tissue, the chronaxy is changing. That means some damage is occurring and hence its excitability is changing. So strength duration curve and using that chronaxy can be used. Now this is called your Rio base. Twice the Rio base you take and that duration is chronaxy. And this, while Rio base is given, that duration is your utilization time. So this is just your strength duration curve. So you talk about what is excitability, talk about your strength duration curve, talk about chronaxy. That is what you do in excitability. The next, you come to all or none law. Define all or none law. What is all or none law? If a threshold or above threshold stimulus is given or not, based on that, the response will be there. When the response is there, threshold stimulus is given, it will respond its maximum. And if it is not above threshold, it does not respond at all. It's a binary phenomenon. When a threshold stimulus is given, it will respond to its maximum. No matter how many times you give it, beyond that or at that level, it will always give the same strength of stimulus, which is maximum. If you give anything below that, it will not respond at all. This is under certain constant physiological conditions. Once you change the constant physiological condition, then maybe the strength of the response might increase, decrease, or not, based on the changes in the physiological environment. Okay, but the thing is, all-in-one law, what does it, apply to? All-in-one law applies to a single skeletal muscle, a single neuron, or cardiac muscle as a whole sensation. What does it mean? So you have a muscle fiber. That muscle fiber is including multiple different muscles. Some muscles, if you stimulate it, it will respond to its maximum. Another muscle also you stimulate it, that will also respond to its maximum. Another one you stimulate, that will also respond to its maximum. But the only thing is, the maximum of each of them are different, based on their size, for example. Okay, so as you increase the strength of the stimulus in this whole fiber, nerve fiber or muscle, when you increase the strength of the stimulus, more and more of them will keep getting recruited. What do you call? Recruitment happens based on their threshold. But each of them will always respond to its maximum. But when you look at the overall property, as you keep increasing, you'll see that the response keep increasing, which should not happen according to all-in-one law. But it happens now only because each of them have separate all-in-one law. As we saw here, all-in-one law applies to a single one, not this whole group. You have to look at each of them individually and see, okay, yes, each of them are obeying all-in-one law. Just that when you take it together, it seems like they're not obeying all-in-one law. So that is what you talk about in all-in-one law. Okay, so cardiac muscle, on the other hand, it is all connected with gap junction. So you stimulate one sensation, the entire thing will act together. Now, conductivity. When you talk about conductivity, when you stimulate a nerve, for example, you stimulate it at rest point. Action potential, which is developing here, can go in two directions. It can go orthodromic or antidromic. So in one direction, we have here axon terminal. The other direction, we have the dendrites. The thing is, whatever going orthodromic will keep going, and the neurotransmitters are there at one level, which contains, these vesicles contain neurotransmitter, and the postsynaptic terminal is here, and it can be taken forward in this direction. So there is signal that gets transmitted, but on the antidromic side, it goes over here, yes, reaches over here, and then what? There is no neurotransmitter containing vesicles over here to go and give it to the presynaptic. So thus, this will die out because there's nowhere for it to go. Okay. Even otherwise, once it is moving from this point to this point like this action potential will never cross back because that is where this is going into hyperpolarization. And how much conductivity is happening is also based on the myelination. For example, in a myelinated one, because of saltatory conduction, it's going to be much more faster compared to an unmyelinated. Okay, so that is what you have to talk about under conductivity. Then you can talk about refractive period. Two types of refractive period. Absolute and relative refractive period. Absolute refractive period and relative refractive period. So this is the point where after the first stimuli, you stimulate a second time consecutively. That period for which the tissue does not respond to a second successive stimulus is its refractive period. Okay, period following an action potential where the tissue does not respond to a second stimulus. That is the refractive period. Now, if it responds, if the stimulus is high enough, that is what you call a relative refractive period. And in absolute refractive period, no matter how strong the strength of the second stimulus is, it does not respond at all to the second stimulus. That is absolute refractive period. So you were talking about your action potential. So in this action potential, you see that your depolarization phase, okay, and 1/3 of repolarization. This is where it is absolute refractive. And below that, it becomes relative refractive. So this is based on the availability of sodium channels. The whole concept of depolarization is because of sodium channels. So over here, we saw that sodium channels were activated. So once the sodium channels are activated, you need to wait for these sodium channels to close and be ready for next activation. So even if it reaches here at this point, just like we were talking about how after depolarization, how we are after depolarization is happening. That slowing down you saw over here. Okay, that is the changes in the flux. And after that, what did we see? A hyperpolarization. So during hyperpolarization, what did we see? There was a lag in opening up of, closing down the potassium channel. So similar to that, even at this phase, there is going to be some time before the sodium channels needs to be closed enough for them to be activated again. So that period is that 1/3 of repolarization. So that is why in this whole time, there is absolutely no sodium channel for you to activate again for a second stimulus. That is why it's called absolute refractive period. But beyond this point, what we see is if we give a high enough stimulus, then some of the sodium channels which were now ready can get activated again to result in a second action potential from that point. Okay, that is your refractive period. So we talked about all-in-one law, conductivity, refractive period. Now, what about accommodation? For accommodation, the prerequisite is you give a slow, gradually rising stimulus. So it should be gradual stimulus. It's not a sudden stimulus like this, but a gradual stimulus like this. When a gradual stimulus is given and it needs to attain its threshold. Okay, so what is going to happen? You give a stimulus. What did we see when you give a stimulus? Usually after the latent period, it goes into potential like this. Instead, now what are we doing? We give a much more slower stimulus. Sodium is coming in, but it's coming in much more slower. It's acting like a graded potential now. Why is it happening? Because regardless of whether the stimulus you're giving is making it reach your action potential or threshold or not, At this point, your potassium channel will get activated, resulting in repolarization. So if it's a slow, gradual stimulus, if you're giving, then by that point, before you reach the threshold for resulting in spike potential, the potassium channel gets opened up, resulting in no action potential. So that is what we call accommodation. And what is infatigable? You saw that in autodromic conduction. It'll keep going, keep going, keep going. There's no energy requirement. What is happening in action potential? You're just opening up an ion channel. Based on its normal concentration gradient, ions are coming in and out. You do not require energy for that. And it'll keep on going till the end. That is why you say that it is infatigable. Okay. What is the property of mixed nerve? Property of mixed nerve is that if you take a nerve, okay, there are different types of nerve fibers. So out of that, there is a Erlanger-Gasser classification, which talks about A, B, C fibers. Okay. A fibers again can be further divided. We'll talk about it in your synapse and all those classes. So you have A alpha, which is the fastest, A beta, A gamma, A delta, B, C. As you go down from here, down, conduction velocity decreases. So the fastest is going to be A alpha. Slowest is going to be C. Okay, so if you stimulate this nerve at this point and you take a recording somewhere over here. At this point, you record. So based on the conduction velocity of them, how are you going to see an action potential? You'll see first A, then you'll see B, then you'll see C. If you further increase the distance, instead of keeping it there, you keep it somewhere over here. The distance is increased, which means now this will not be like this anymore. It will further A alpha, A beta, A delta, considering it's a sensory. So we see A alpha, A beta, A delta, B fiber, C fiber. So as you increase the distance, what happens is the difference becomes more drastic because it's covering a long distance and the gap between them keeps increasing. So this is a compound action potential that you see in a mixed nerve because of the difference in the conduction velocity of them. Okay, that is the property of your mixed nerve. So this is the most important ones that you need to talk about in your exam. So this is also a very important question. Your action potential again is a very important question, and sometimes RMP also comes. Okay, so that is it with your nerves. I'm just going to continue ahead with your neuromuscular junction. Again, draw a neat label diagram of neuromuscular junction. That is a very important question. Okay, explain the steps in conduction across neuromuscular junction. That is another question. Then, often asked question is myasthenia gravis versus Lambert-Eaton. Lambert-Eaton syndrome versus myasthenia gravis. Or sometimes separately myasthenia gravis can be asked, or separately Lambert-Eaton can be asked. These are the questions that you have to learn in this chapter. So in neuromuscular junction, you're taking it out for study, learn how to draw the neuromuscular junction. 2, you understand the steps in the conduction across the neuromuscular junction. 3, we talk about myasthenia gravis, Lambert-Eaton syndrome. That is all you have to study in this chapter. Okay, so you can see here, nerve terminal bottoms, basal lamina, okay, and it is going out into the post-junctional folds. Now this is where you have to draw this like this. So when you're drawing it like this, you draw the terminal here like this. The postsynaptic terminal, throw it into multiple folds like this. Okay. Now, through the microtubular system, different types of vesicles are going to come in. You have to draw mitochondria because energy requirements needs to be met over here. Okay. There's one P by Q type of calcium channel which is important. And we have the vesicles. These vesicles at the neuromuscular junction has acetylcholine, usually around 6,000 to 10,000 acetylcholine molecules. Now they go to certain areas called the active zones and arrange themselves as doublets. So they go to the active zones, arrange themselves as doublets, and from here they go into the neuromuscular junction. Thus neurotransmitters will go to the postjunctional fold. Okay, and in the postjunctional fold, in this area, this is where your nicotinic muscle type receptors are present. Acetylcholine will combine with the nicotinic muscle type receptors, thus resulting in an end plate potential. So something called an end plate potential, which is similar to a graded potential here. And once the end plate potential reaches its threshold, it will activate a voltage-gated sodium channel, resulting in influx of sodium. And action potential will finally continue here. So the action potential which was in your nerve, which got carried all the way, that action potential will result in calcium to come in. Now, once calcium comes in, calcium will combine with the neurotransmitter vesicle to allow it to come here, fuse, and release its neurotransmitter. The neurotransmitter containing acetylcholine is going to go to the nicotinic M-type receptor. That will result in what you call the end plate potential, which is a graded potential. Once it reaches the threshold, it will activate a voltage-gated sodium channel, resulting in influx of sodium, and hence depolarization wave has reached here. Okay. Now, again, these steps, you do not need to know this much in detail. All you have to know is, yesterday we were talking about it. We have T-snare and V-snare proteins. Okay, so synaptogmin is what calcium combines with. V-snare and T-snare, they bind together with the help of Rad GTP and form a ternary complex. And another thing called the synaptophysin will help in fusion and will release it. So in the sequence of NMG, draw the NMG, explain the steps in transmission across the NMG. These are the things that you have to talk about. Okay. The next question is myasthenia gravis versus Lambert-Eaton. So first you have to talk about where is the abnormality. In myasthenia gravis, the abnormality is in the postsynaptic terminal. In Lambert-Eaton, the abnormality is in the presynaptic terminal. In the postsynaptic terminal, where is the abnormality? Myasthenia gravis. It is an autoimmune disorder where autoimmunity attacking its own cell. So what part of it is getting attacked? The NM type of acetylcholine receptor we saw. Nicotinic muscle type acetylcholine receptor. On the other hand, Lambert-Eaton, what is the problem? The P by Q type of calcium channels in the presynaptic terminal. So the post and this is the presynaptic terminal that is getting affected. So as a result of that, what is the problem? Myasthenia gravis, once acetylcholine comes, binds to it. Okay, and you keep doing it, you see that, and not all the acetylcholine receptors are available because autoimmunity and destruction of them are there. So as you keep doing it, the amount of acetylcholine receptors which are available for acetylcholine to bind will be lesser and lesser. So they will have fatigability when they do repetitive tasks. So for example, they wake up and they're fresh, they keep doing stuff, and by evening they're very tired. They do their work, they're washing dishes, and after a point they feel very tired. So they tire out by repetitive activity. Okay. On the other hand, in Lambert-Eaton, what is the problem? The calcium is not coming in much. Okay, and calcium is not there, not enough vesicles are released, and because of that, they are tired. But when you keep stimulating them, at some point, enough calcium would have come inside in order to allow enough neurotransmitters to cross, which point they are no longer fatigued. So here it's the exact opposite that is going to happen. Repetitive activity will result in increased strength. Otherwise, normally they are tired. When they start doing few times they're tired, but by repetitive activity, they develop strength. Okay, then investigation. So for myasthenia gravis, you do something called the hydrophonium test. So in hydrophonium, what we do is we give a acetylcholine esterase. So acetylcholine esterase, what does it do? It breaks down whatever acetylcholine is there and takes it back. So acetylcholine esterase inhibitors, if you give, whatever acetylcholine is there won't be broken down. Instead, it will last there longer, resulting in more activity. So when you give hydrophonium for a short period of time, you will have good activity. Okay, or you can check for radioimmune assay to see how much of autoimmunity, autoantibodies are there. You can do an EMG. You can either do a single fiber or repetitive. So in repetitive, what do you see? You repetitively do the EMG signal. When you repetitively do, the amplitude decreases. Okay. On the other hand, Lambert-Eaton also similar thing. You do a radioimmune assay to see what type of antibodies are there. And here repetitive means the amplitude will increase. And in both of the cases, you generally tend to do some scans. You see thymomas in myasthenia gravis. Usually, cancers, especially of the lung, are seen in people with Lambert-Eaton. So that's why you do these scans. Okay, so how do you treat these two? The problem is, we were talking in a hydrophonium test. So you see that anticholinesterase can help inhibitors if you give. Okay, so this anticholinesterase, for example, pyridostigmine can be given. Or the problem is autoantibodies. You do plasmapheresis, that is, take out some blood, filter it out, remove it of the antibodies and give it back. So thereby you're removing your autoantibodies. Or you give immune therapy or immunosuppressants, because the problem is your immunity is a problem. So you give an immunotherapy or immunosuppressants. Okay. On the other hand, in Lambert-Eaton, one thing you can do is, again, plasmapheresis, just like that, because autoantibody is a problem. Or you can give an immunotherapy. Again, autoantibodies are the problem. Or you can give aminopyridine. Okay, so this what it does is it presynaptically inhibits the voltage-gated potassium channels, and that seems to somehow stimulate the calcium channels. Okay, so these are the various questions that we have covered today. Of that, the most important questions are, what is RMP? Okay, just for you to understand what are the questions. RMP you have to learn. Action potential you have to learn. You have to define action potential. Okay, you have to draw. Then the mechanism of different phases. Then you have to talk about the properties. Then you talk about the neuromuscular junction. And in neuromuscular junction, you have to again draw the mechanism of transmission, then myasthenia versus Lambert-Eaton. So these are all the questions that you need to at least study and go for your exam for your neuron. Okay, now chapters. So we'll just wrap it up by understanding a little about the Auricle app. So Auricle's got foundational classes where pre-recorded sessions are available. There are live sessions for you to have a one-on-one interaction with your teachers and ask doubts and learn. There is an express exam module, which will help you prepare right before the exam, where just like how I was teaching today, exam-oriented questions and its discussion will be there. There's one-to-one doubt clearing sessions, and you can get hard copy notes as well. There are also question banks of various difficulties, which will not only help you for your professional exams, but also in the future for your NEPG and FMG. Practical sessions are also pre-recorded and made available. These are the various subscription plans which are there currently, and you can use my code of Shakthinag 20 for discount on your subscription. Thank you for watching. In case you need to contact Team Auricle, you can feel free to look them up in any of these social media handles. So thank you.